So we're given a circuit with two switches and two capacitors. Tells us that switch 1 and 2 have both been in position A for a long time at t equals 0. And then at t equals 0, they're moved instantaneously to position B. So in other words, switch 1 is like this, switch 2 is like that. So what we should notice is that the capacitors at this point are not connected to each other. And since we are also told that these switches have been in position for a long time, we can convert both capacitors to open circuits and solve for those voltages individually. So I'm going to do t less than 0 for C1 first.
When I'm drawing it though, couldn't you see that you're going to need something else?
Elaborate. Like, what do you mean?
Like, because they're open on both sides.
Yeah.
So, would you, like, have to do that integral stuff again?
No. You only do an integral if it's a current source in series with a capacitor.
Oh, okay.
Or a voltage source in parallel with an inductor. Or short circuit in parallel with an inductor.
I need to remember that.
Okay, so this is 100 volts, 10 kilo ohms, right? And then this is VC1 of 0. So what's VC1 of 0?
100? No.
Hmm?
No.
Trust your gut. Trust your gut. You sure?
Let me think about it.
Hmm? Mhm.
KVA.
100. You said it.
I don't know. I was just so. Because there's no current going through.
You just gotta trust your big brain. VC1 is 100 volts. All right, now we are going to draw the circuit for t less than 0 for capacitor 2. Right? And remember, the capacitor tells us its polarity. So we have to define it like that. Now, what is the voltage? VC2 of 0. Yeah. Negative 200. Do we all see that?
Yeah.
We understand why it's negative?
I'm putting the positive probe on the negative.
Yeah.
Turn this love.
And there you go.
Yeah.
Applying what you know, bro. That's what it's all for. All right. So now we have our initial conditions. Now, let's look at what the question is asking for, because that can always sometimes save us some work, right? So part A asks us to find the power delivered by VS2 as a function of time for t greater than 0, right? So once the switch flips, the switch is in position B there, and this switch is in position B here, right? So both capacitors are connected to each other. That's one thing we need to note. Another thing we need to note is that Vs of 2 is also connected to those capacitors as well, which means it's going to be time varying, or the current through it, I should say, is going to be time varying, which means we're going to have to solve for the equation for the voltage across the capacitor, right? It's inevitable. But in like the off chance that this battery was disconnected from the capacitors, then obviously it's super trivial. That's not the case though, unfortunately. It never is. So now we're going to redraw the circuit for t greater than 0. And so now this is our circuit. Okay, that's 200 volts, 5 kilo ohms, and yeah, that's our circuit. And this is VC1, VC2. Okay, now typically at this point, right, the goal is to find VC of infinity. But let me show you what happens when we apply steady state conditions to these capacitors. Turn both of them into open circuits. And you see this little part right here? That's what we call floating voltage point, I believe is what it's called. Because it's disconnected from the circuit, which means we can literally take this and move it anywhere we want, right? Because it's not connected to the circuit, it's not going to change the voltage. We can't have that, right? That's not allowed. There's no way we can solve for a voltage across a floating wire. So we're going to have to do something different. Now, lucky for us, I hope you can see that these capacitors are in series. How long has it been like that?
Like 2 seconds.
Okay.
Three bars in a series.
So what are we doing? How do we cut the problem?
Gosh, dude, I was actually going to crash out. Okay. All right, yeah. So we're going to have to combine them in series. Now, does anyone remember how we combine capacitors in series?
Is it just voltage, right?
Like,
Isn't it just like we treat it like a like negative VC1?
like voltage, like adding voltage sources in series? So that's how we are going to find our new initial condition. We're going to add those together. We can combine those like voltage sources, right? But I'm talking about actually combining the capacitors together in series and solving for the new capacitance.
Like it's parallel, like you just added like parallel.
Yeah, exactly. So C1 is 3 microfarads, C2 is 2 microfarads. So C equivalent is equal to 2 times 3 over 2 plus 3 microfarads, which is going to be 1.2 microfarads. Right, so this is our new capacitor. And now we can convert this to an open circuit and solve for VC equivalent of infinity. Right, so this is going to be VC equivalent of infinity. And we're going to convert it to open circuit, steady state. And this is still 200 volts. So VC of equivalent. And remember, this is a new capacitor, so we can define the voltage however we'd like. This is not given to us. And the way I have defined it, we can say that VC equivalent of infinity is 200 volts. But now we need to find our new initial condition, right? In order to do that, we need to, like Muhammad said, add the voltages of the capacitor's initial conditions that we solve for individually together. But we need to do so with respect to the polarity that we have given C equivalent.
Not how I did it.
So, in other words, we need to keep this polarity, which means we can take VC1 of 0 and subtract VC2 of 0. Because
subtract them because both polarities are facing the same way. Like plus plus.
you would subtract VC2 of 0 from VC1 of 0 because VC1 of 0 has the same polarity as this new C equivalent that we have defined. So in order to keep this polarity, we treat this as a positive and treat VC2 as a negative. So in equation form, that looks like this. 0 minus VC2 of 0. And you can think of that, you know, sort of like this, right? Whoa. Whoa. Can I not rotate? It's kind of lame. Oh, yeah, I can. Like rotating it along like this. You see how it's going the opposite direction of the other one? We're going to subtract it. Okay, so that means VC equivalent of 0 is going to be 100 minus negative 200. .300 volts. All right, now the last step is to just find our time constant with respect to our equivalent capacitor. So I'm going to redraw the circuit for t greater than 0. And we're going to do our equivalent method, so we're going to short out the battery. So all we're left with is this 5 kilo ohm resistor. So of course our equivalent is just going to be 5 kilo ohms. And so tau is going to be 1.2 microfarads RC times 5 kilo ohms. Right? So it's going to be 6 milliseconds. I think. Double check that. Yeah, 6 milliseconds. And so now we have everything we need to write our VC equivalent of T equation. 200 volts plus 0 minus infinity, so it's going to be plus 100 volts, times e to the negative t over 6 milliseconds. That is for t greater than or equal to 0. That all makes sense. Not too bad. So now we need to start approaching part A, right? So I'm going to redraw our circuit for t greater than 0 with the capacitors combined. So that's going to be 200 volts. That's going to be 5 kilo ohms. And this is VC equivalent of T. And the question wants us to find the power delivered by the 200 volt voltage source as a function of time. Keyword there, as a function of time. And that makes sense, right? Because the power delivered by VS1 is going to be V times I, right? Where I is constant, But I, the current leaving the battery, is time varying. Therefore, power delivered will really be a function of time, where V is a constant, 200 volts, and I is the current leaving the battery. Now, what else could we say about this current? What else could we call it?
IFT?
It's a function of time, but what?
Negative ICFT.
Is it? Would it be negative or positive?
Oh, positive.
Yeah, positive.
Yeah.
Because it's positive to negative, as a passive component should be, right? Capacitors are passive, so positive current flows from positive to negative terminal. Or that's the sign we give it at least, right? So 200 volts times IC of T. Because this blue current, which is IS, is also IC of T, or IC equivalent of T, I should say. And solving for IC of T is going to be really easy, right? We can just use our capacitor property, C dVC over dt, where C is C equivalent, of course. So it's going to be 1.2 microfarads times the derivative of an exponent. It's going to be negative 1 over 6 milliseconds. And now the derivative, the whole thing, obviously, which is 200 goes to 0. And so we're just left with 100 volts e to the negative t over 6 milliseconds. 1.2 times negative 1 times 100 divided by 6 times 10 to the negative 3. So it's going to be negative 20 milliamps e to the negative t over 6 milliseconds. And that is for t greater than 0. That is our equation for IC. Let me just double check my units there. Times negative 1 times 10 to the negative 6 over 6 times 10 to the negative 3. Yes, okay. So now we can solve for the power delivered as a function of time to be 200 volts times what we just found, negative 20 milliamps e to the negative t over 6. So it's going to be 200 times 0.02. So it's going to be negative 4 watts e to the negative t over 6 milliseconds. Make sure that's good. Yes.
Real quick, how do you define your current again for IS and IC?
So since it's asking for power delivered, we're just going to go ahead and define this current IS, right, to be leaving the positive terminal of the battery. So we can just simply say that power delivered is equal to positive Vs times Is, right? What we also noticed is that this current Is is the same current that is entering the positive terminal of a capacitor. So we can say that Is is equal to Ic. So yeah, that's what's going on there. And all right, that's part A.